Hi, Biochem 141. So the atomic mass is an important concept in chemistry, and we're going to learn how to calculate this. Um, so the atomic mass of a single atom is very, very tiny. A hydrogen atom is 1.63 times 10 to the minus 24 grams. So it's really not convenient to work with those numbers. And recall a hydrogen atom has one proton and one electron, no neutrons. Unless it's deuterium, then it would have double this mass. So that's the weight of one proton. You can see that on this table here. 1.63 times 10 to the minus 24. So, and that's in the nucleus of the atom. Neutrons are also in the nucleus and they have weight 1.6575 times 10 to the minus 4. The electron is much smaller, so you basically consider that to have zero weight. So to make it convenient, what we do is say that 1.6 times 10 to the minus 24 is 1 AMU, so atomic mass unit. So anytime you have a proton or a neutron, that's equal to 1. So you could kind of rewrite this table. Proton, neutron, electron, charge. Protons are positive, neutrons are 0, neutral, and electrons are negative. Mass, protons are positive, protons are 1 mass, AMU, neutrons have 1 AMU, and electrons have 0. So that's just how we're going to think about calculating the mass. So the atomic mass number is what tells you the mass of the element, and that's in atomic mass units. The atomic number, that tells you the number of protons. So you're able to determine the number of neutrons with the atomic mass unit, because the atomic mass unit has protons and neutrons. So considering carbon, the atomic mass unit is about 12. So that's proton and neutron. So if you subtract out the 6 protons from the atomic number, then you know you have 6 neutrons. So that's kind of how you can determine how many neutrons there are. So looking at copper, the atomic mass is approximately 63.55. So let's round that to 64. So that's proton and neutron. So how many neutrons are in here? How many neutrons? Well, we know there's 29 protons from the atomic number. So if you take the difference of those, because only the protons and neutrons carry the weight of the atom for the relative mass calculations, that's 35 neutrons. So that's kind of how you do that. So the average atomic mass, some copper might have 65, some might have 63 atomic mass. And that's based on the number of neutrons and protons. The number of protons stays the same. So for copper, we have 29 protons. So copper 63 minus 29. 63 minus 29 is 34. So this one has 34 neutrons. And copper 65, if you take the difference there, 65 minus 29, that is 36. 36 neutrons. So what they do is they take the average of what they find in nature, the abundance, and so that's where you get this 63.55 value. It's an average of the two different isotopes, which have different numbers of neutrons. So when you look at the periodic table, you see the average atomic mass unit. So with the one you might see behind me here, if you look on the bottom part of the atom, that's where they put the AMUs. So for this periodic table, let's look at this one here. You can see all the atomic weights on this. So oxygen, 15.9, fluorine, 18.998. This one goes out to many digits here. We don't need to really go that far for them. So that's a lot of information here on the periodic table just with the atomic mass unit and the atomic number. So you could figure out how many neutrons are in any of these on average. So let's look at magnesium. So 12 Mg 24.3. That's the average atomic mass. And it's 24.3 because some magnesiums might be 24, some might be 25 or 26, maybe some are 23. I don't actually know those percentages. You could look that up for magnesium. Just looking at that, it's kind of an estimate, maybe 80% are 24 and 20% are 25. Who knows though? You'd have to do the mass spec for that. So looking at this, it's 24 about minus 12 for the protons. So this is proton and neutron. And then subtract the protons. So that gives you the number of neutrons. So that tells you there's 12 neutrons for magnesium. So I'll throw in some practice problems for that tonight for you guys. And then keep this table handy here. So now let's consider the mass of molecules. So the mass of atoms is easy. You can say, oh, what's the mass of titanium? And just zoom in here. Titanium is, it's not really zooming in well, but 47.88. So that's the weight for titanium. Now you could also, let's look at this molecule here, chloroform, CHCl3. Now that's a subscript here, the numbers on the bottom. Subscript. So that tells you there's 3 chlorines. There's an implicit 1 here and a 1 here. They don't write them on these molecular formulas, but just know that that's what that means. 1 hydrogen and 1 carbon. So that chlorine, you can go look on the periodic table. Chlorine's 35.5 approximately, if you round that. Or 35.45 for this example. So times 35.45. Hydrogen's about 1.008. And the carbon's about 12.01. So now we want to do the math for this calculation. So 3 times 35, because there's 3 chlorines, is 106.35. 1 hydrogen, that's 1.008, and then 1 carbon, 12.01. And then you can add these up. I should have lined this up for sig figs. 106. Let's see, what is that? 106.35. So this decimal goes 3 digits past the decimal, and this number goes 2. So that's where you're going to cut your sig figs off, is 2 after. So then you just add these up. 106.35 plus 100.008 plus 12.01, and then you get 119.368. So now consider sig figs. This last column we don't include, so it ends up being 119.37 atomic mass units. And then also sometimes you mention atomic mass units in grams per mole, just so you know. We'll get into that later. So that's pretty simple how you calculate these. You just have to be aware of the formulas. So we'll do a little more, maybe there's another practice on here so we can go through that. Yeah, let's look at this molecule, aspirin. So aspirin is C9H8O4. So now we know there's 9 carbons and they're 12.01 AMU off the periodic table, the molecular weight. And there's 8 hydrogens times 1.008 and 4 oxygens times 16 for the molecular weight there. So then you just add those up after you multiply them, and that will give you your molecular weight. So 12 times 0.09, 12.09 times 9, 108.81. 8 times 1.008 is 8.064. And then 4 times 16, 64.00. So, and again, this goes 3 past, 2 past, 2 past the decimal. So this, you end up chopping that off there. 108.81 plus 8.064 plus 64. So you get a lot of practice with your calculator and adding these guys up. 180.874. So now the 4 gets dropped off. So it's less than 5, so you don't round it. So I'm not sure how my number was a little bit off of theirs. Let's see here. 9 times 12.01. I don't know, this was not an 81 somehow. That was a 09. That was where my little mistake was there. So 108.09 plus 8.064 plus 64 is 108.154. And then again, chop that off is this decimal goes. I'll line that up here, make it look nicer here. There we go. So anything that goes past where the lowest number of decimal places past the decimal, units places past the decimal, that's where you chop the sig figs. All right, so that's aspirin. And then I think that's enough for now. Maybe let's do one more with the polyatomic ion, since I just mentioned those. How about sodium or magnesium carbonate, MgCO3 2 minus. I want to get one with parentheses here, so let's not use that one. That would be MgCO3. So let's look at sodium carbonate. Carbonate's 2 minus, so this 2 goes down here. Na2CO3. I want to get one with these parentheses, so let's do this. How about magnesium hydroxide? It's 2 plus. So this 2 will drop down over here. So MgOH2. So that 2 is being applied to both of these. That's why I was trying to get this parentheses here to show you guys how this works here. So it's Mg times 1, oxygen times 2, hydrogen times 2. So magnesium is 24.305. Oxygen is 16.00100. Hydrogen is 1.008008. And so the oxygen, you got to multiply it times 2. So that's 32. So 32 plus 24.305 plus 1.008. 24.305 plus 32 plus 1.008. And that gives you 57.313. So that's the magnesium hydroxide. And then finally, I want to get one example where that parentheses is a little bit more complicated, where we have to kind of distribute it. So I think a good example would be maybe phosphate, PO4 3 minus. Make sure it's phosphates, right? Yeah. Okay, so phosphates, PO4 3 minus. So let's say we have magnesium phosphate. So magnesium is 2 minus. So this 2 carries over down there, and then the 3 drops over here. So you get Mg3PO4 2. So this is where it gets a little tricky. So this 2 has to get distributed to both of these within the parentheses. So you have magnesium times 3, phosphorus times 2, and then oxygen. It's not 4 and it's not 2, it's times 8, because 4 times 2 is 8. So 8 times 16.00. Phosphorus is 30.97, about 2 times 30.97. And then magnesium is 24.305. And then we'll just make that 0.31 because keep the sig fig simple that way. So 3 times 24.31, 72.93. 2 times 30.97, 61.94. And then 8 times 16 is 128.00. Then you add these up, and you get 262.87. And so that's how you do polyatomic molecular weight. And I think that should kind of cover it. I hope there's no struggles with this. Let me know if there's a molecule that you're trying to find the molecular weight for and it's kind of confusing. Just remember that the subscripts mean that the numbers in front, numbers multiplied by that value. And then if there's parentheses and a subscript, like in this particular case, then you have to distribute that subscript. Okay, so.